Alright, in this video on equilibrium, we'll look at some applications of the equilibrium constant. The first one we'll look at is in a situation where you might be given some data about reactants and products, concentrations, pressures, and you don't know if you're at equilibrium or not. You know the equilibrium constant, but you're not sure whether these concentrations actually fit the equilibrium constant's values or value or not. Well, in this case, you calculate something called Q, capital letter Q. Q has a fancy name. It's called the reaction quotient. And the reaction quotient, or Q, is also known as calculating K, but you might or might not be at equilibrium. And so the general form for calculating Q is products, concentrations, or pressures, to the power of its coefficients divided by concentration of reactants, or reactant, to the power of its coefficients. And there might be more than one. Multiply them together. Might be more than one. Multiply them together. And so Q is really handy because it can tell us, are we at equilibrium or not? In sample exercise 15.9, which we'll do in just a second, we're going to answer the question of find Q, and then are we at equilibrium or not? So to figure it out, you have to compare the value of Q to K. If Q equals K, well, then you're at equilibrium. Q and K are the same. You have the correct amounts to have the product divided by reactant ratio to be the same. If Q is greater than K, well, then that means that the product side is too great. The top of the ratio, or the top of the fraction, the numerator, is too large. If Q is less than K, well, then there's too much reactants. And so the reactant would have to shift or change to get rid of some of that reactant. It's just like right here, if there was too much products, the reaction would have to shift or change to achieve equilibrium by getting rid of some products. Alright, so with that as a background, pause the video now if you need to write any of these notes down yet, and I'm going to put the sample problem up. The sample problem we're going to work is this one right here called Predicting the Direction of Approach to Equilibrium, sample exercise 15.9. So here's the equation that's given to us. H2 plus I2 goes to HI, all gaseous. And it gives us the K, and it tells us it's 50.5, and then it's going to give us some concentrations of reactants and products. And it wants us to predict the direction that the reaction would have to proceed to achieve equilibrium. In other words, it's saying, are we at equilibrium or not? Is there too much products? Is there too much reactants? Or are we at K right now? Well, it gives us a bunch of values down here, and I'm going to go ahead and do some of the math, but I'm going to let the book do some of the math for us as well, and you can pull out your calculator and follow along if you want to do some of that as well. So the first thing we need to do is write down what the reaction quotient is, and it would be products, HI, to the second power, because there's a 2 right here, divided by reactants, which would be H2, times I2, both to the first power, because there's just 1's in there for the coefficient. And then whatever the concentrations are, we need to plug those in. We don't know whether it's at equilibrium or not, so we can't make an ice table yet and say, oh, we're only going to plug equilibrium values in. We just plug in whatever values they get us, and then we'll compare that number to 50.5. So they give us some data right here, and they say we start with this many moles, this many moles, and this many moles in a 2-liter container. So what we want is to find the concentration. And remember, molarity is equal to moles divided by liters. And so to find the molarity for each one of these, we would take the moles of HI, which is 2 times 10 to the negative 2 moles, and divide it by the size of the container, which is 2 liters. And we take the molarity of the moles of H2, which is 1 times 10 to the negative 2, and we divide that by 2 liters. And then to find the molarity of I2, we would take the moles, 3 times 10 to the negative 2, and divide that by 2 liters. And then we'd have the molarity of HI, H2, I2, And then we could take these numbers and plug them in here. So instead of struggling a lot by punching the buttons on the calculator, let's just look down here. HI ends up being 1 times 10 to the negative 2 molar. H2 ends up being 5 times 10 to the negative 3 molar. And then the iodine ends up being 1.5 times 10 to the negative 2 molar. So these numbers now end up going into our Q expression to find out where we're at. So HI ends up being 1 times 10 to the negative 2, and that's squared. And then H2 ends up being 5 times 10 to the negative 3rd to the first power times 1.5 times 10 to the negative 2nd for I2. And then we punch that into our calculator, and you end up with 1.3. Don't forget to square that one right up here. Now, this is Q, and we have to compare Q to K. And a lot of kids struggle with this. Remember that when you're comparing Q to K, take your K and write it over 1. This is our K. Now take your Q and write it over 1. And then say, what do I have to do to get the top to look like the top? Oh, okay. So the products have to get larger to get to look like K. That means I will need more products to get to K. And so the fancy way to say this is that the reaction would need to shift or change or produce more products to achieve equilibrium, because right now I don't have enough. So there's an example of Q, the reaction quotient, using to predict the direction the reaction has to shift in order to achieve equilibrium.